Okay. It's possible. It's possible, but I put a post on there. If I put on the simultaneous problem on the test, then actually solving it numerically would be a bonus. But you should be able to recognize when you need to do simultaneous and when stepwise is okay. And so that's the most important thing. If you just go ahead and do a simultaneous problem stepwise and leave your answer as that, then you would lose points.
For simultaneous, can you do like the setup again? I was trying to do the problem here, but
the setup?
But I wasn't understanding what's going on.
The setup for simultaneous? What do you mean the set? Like
when you do it simultaneously,
right?
You have the ammonia, and you have
like I set up the problem earlier. You mean beyond that, or just setting it up, the basic setup for simultaneous? I mean, for the ammonia, was there any problem following the setup with that, or not understanding what's going on? With
I talked to people and they don't know.
With the simultaneous, yeah. Simultaneous is a challenge problem, sure, but for the ammonia, was anybody able to do that? Or actually, let me ask you this: how many people read through the problem again? So just 2 or 3, 4. All right. Out of those, how many people tried to repeat the problem up to the point and were successful? You couldn't do it by yourself then, basically. How many people were able to do the simultaneous in the homework? Actually, how far are you guys on the homework? Finished it? What did you do with the 2 simultaneous problems in the homework? Look at the solutions manual. What did I say about the solutions manual on that? It was wrong. What did the solutions manual do wrong?
It said 2 different K values for the same.
Okay, that's one thing. They got 2 different K values, but the primary thing that they did wrong was they really didn't even do it stepwise. I mean, they did the stepwise proper. They didn't even follow that because they assumed what? Whoever, the problem with the solutions guide is we got a lot of different people doing that. The answers aren't really checked over thoroughly. So there are a lot of errors sometimes in the solutions guide, but you should be able to find those. This one in particular, because what did they do? Actually, how many people looked at it? What problem number was that? 89. 89. How many people looked at the solutions guide? And these things always come up, and so these things are best to take care of sooner. Because if right before the test, you still don't understand, like I said, repetition is the best way, but if you saw it and you understood it and you reviewed it, 2 or 3 times before the test, then it's pretty easy. Actually, the test should be pretty easy, But what exactly does the book do? So let's set up it correctly. What was the problem?
It was 0.100 molarity ammonia.
Oh no, for number 89.
Oh,
1.0 times 10 to the
Okay, 1.0 times 10 to the minus what? 5. Hydrocyanic acid, or HCN, hydrogen cyanide. And so how do you set this up? Well, obviously we want to do this stepwise. So you pick out the biggest K value first, which would be Ka. Right. What is the Ka for HCN?
6.2 times 10 to the negative
6.2 times 10 to the negative
10.
10. So that's bigger than water. Water is like 10 to the minus 14, so we'd start with this. So 1.0 times 10 to the minus 5, you start to worry about this problem because of low concentration. You know, and it's a weak acid. It's not one of the 7 strong acids. Start to worry about it. So I'm just going to write this, you know, quadruple 010 molar.
So when we see that, we recognize that we have to do simultaneous.
No, you might not. 10 to the minus 5 might be okay.
So it's -7, -8.
Well, I don't know. The thing is, the number, you know, the number is just a guideline. It just as a warning flag, but you need to check it yourself to make sure, right?
But if we're running out of time,
if you're running out of time, still you don't really know. We're warned. It could potentially be simultaneous, right? But it might not be. Depends. So you just do it. What do? You know, it's just following steps. A lot of people get stuck because, but you know, there's a method to this. And the method is what? We try stepwise first. If stepwise fails, then we go to simultaneous. I don't automatically go, oh, stepwise is going to fail here. I just go ahead and try it and see what happens. And so doing this stepwise shouldn't be too difficult, right? Is that straightforward to do this stepwise?
Yes.
Yeah. Did anybody do this on stepwise?
No.
And what happened with the stepwise?
You get 7.9 times 10 to the negative concentration of hydrogen.
Okay, in step 1? Okay, and then in step 2, what happened? Did you add a significant amount of hydronium or not?
yeah.
Wait,
Where was the trip up for the ammonia? I mean, I know when you do a blank page, this is why I like to see a survey, because I don't, you know, sometimes I don't see where people go down the wrong, because there are multiple places you can go wrong, you know, multiple places you can go wrong. And so when you try to repeat the ammonia, you should try to repeat the ammonia problem that we did, you know, from scratch. And when you did that, where did you get tripped up, or where did you get hung up, stopped? You know, you got to think about it. Where was it that you got stopped? A lot of people don't even. I know only a few people saw it, so I'm talking to you guys. You know, for the rest of you that didn't even attempt it, you know, you're really putting yourself at a big disadvantage, you know, in the academically, because, you know, the first problems you should do are not the homework. The first problems you should do are the ones in class. You know, to repeat those are the most important. And then if you haven't even gotten to those, I wonder what's happening with the homework, you know, because tomorrow's the test, and you know, there are trade-offs. Sometimes you go, well, you know, the simultaneous is advanced. If I skip it, how many points could I potentially lose, and can I live with that, you know? Well, for a lot of people, that's fine. That's a fine trade-off. You don't want to spend all your time just studying one problem simultaneous and sacrifice everything else, you know? And so if simultaneous is like hitting a brick wall, then just skip it. Focus on the basics. If you can do the basics, you'll get most of the points, right? And the basics are just the stepwise standard ICE. If you can't do this, you know, like a 2-step, 3-step, 4-step, it's trouble. Sure. So, well, let's do this then. Minus x molar, plus x molar, plus x molar point. quadruple 010 minus x. That's smaller, that's smaller. And then the Ka for this is just going to be the hydronium times the cyanide divided by the HCN. It's going to be x squared over point 0.010 minus x. Then we just automatically try the simplifying assumption. So this is going to simplify x squared point quadruple 010. I don't even want to think, will it work or won't it work? You know, how many minutes do you want to spend debating if it's going to work or not? You know, when it's so easy to do, you might as well just punch it out. Is my opinion. Sometimes, you know, after you see enough of these, you automatically go, it's not going to work. Skip it. Save a little tiny bit of time. But anyway, this comes out to x equals 7.8 times 10 to the negative 8. 7.8 times 10 to the negative 8. And so let's go ahead and calculate the percent change, which is 7.8 times 10 to the negative 8 is the change x over the initial times 100. This comes out to what? 0.78%?
Yes. Yes.
Wow. That means it's okay. It's okay. So, you know, HCN is an especially weak acid. It just doesn't generate much hydronium. It's a very little hydrolysis here. And so even though this initial concentration is so small, it still worked out okay. So this is quadruple 010 minus, and how many zeros? I need 7 zeros. 1, 2, 3, 4, 5, 6, 7, and then a 7, 8. This is what, 780?
Yeah.
Yeah, I'd like you to carry one extra digit. You know, I need to see how it was rounded. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so we got 10 minus 8 is 2, 9, 0, 0, 0, 0, 0.
No.
And then all right, then what do we do? No, before we do step 2.
Like K.
Check K. Does K check out?
Yes.
Yes.
Yeah, it has like 6.13
6.13.
10 to the negative 10.
It's a little off,
Up.
but probably due to round off.
Round.
Yeah. This is okay, maybe. Hmm? Yeah, now we do water. That would be step 2. And so H2O liquid plus H2O liquid. This is an acid solution, so we got to figure out all the hydronium ion contributors, and water is going to be one of them. Hydronium plus hydroxide. So what's the initial here for hydronium? Yeah, 7.80. Let's just carry that over. 7.80. times 10 to the minus 8 molar. So this is one of those paths that people, I see. The people who are really shaky on the two-step process forget to carry the hydronium ion concentration down and start with 0 and 0. Right? All the time, I see this. How about the hydroxide? 0. And so let's see how much additional hydronium we generate. Plus X molar, plus X molar. 7.80 times 10 to the minus 8 plus X molar and X molar. It's all for KW. It's all for KW. KW is the hydronium times the hydroxide. 7.80 times 10 to the minus 8 plus X times X equals 1.0 times 10 to the minus 14. Should we do the SA? We could do the SA. We could do the SA, but this is one of those things. I'm trying to give you an idea about if the hydronium's like this, 10 to the minus 8. Do you think water will be a significant contributor or an insignificant contributor? Significant contributor. Yeah. And so here's a case where I would just skip the SA and just go straight to the quadratic, because we've talked a lot about this already. And we did some calculations to show that it is significant. So somebody have a quadratic solver? What was it again? 6.82 times 10 to the negative 8. Yeah, that was a significant. Look at it. About half of it came from hydronium, half of it came from water. And so this is going to be 7.80 times 10 to the negative 8 plus 6.82 times 10 to the negative 8, which gives me a total of 14.62 times 10 to the negative 8 molar. And so we just about doubled the amount of hydronium by KW. Now, what did the book do wrong? What did the solutions manual do wrong? Did anybody carefully look at the solutions manual? What the solutions manual did wrong was they decided what X is. You know what they called X? They called X 1.0 times 10 to the minus 7. And so they just added 1.0 times 10 to the minus 7 here and 1.0 times 10 to the minus 7 here. Do you know why they did that? Because that's in pure water, that's what you get, right, from hydrolysis or autoionization. But what's the problem with that? This is not pure water. In fact, this has hydronium to begin with. And can you build up the population of hydroxide to that same high level, 1.0 times 10 to the minus 7? You can't build it up because, okay, you explained this to me in the words that I said earlier. Anybody review that? Predator-prey, that's one way, or Le Chatelier's, number 2, inhibition, or the common ion effect. Those are 3 ways to explain the same thing. There's no way you can build that up to 1.0 times 10 to the minus 7 molar, right? Not with a little bit of hydronium there present. Does that make sense? And so the book is definitely wrong on that. And then, not only that, they add 10 to the minus 7 molar. If you add 10 to the minus 7 molar, that's 10 times 10 to the minus 8 molar. And so we go from, all right, 10, we go to 17.8. 17.8, and then they call that the final answer. 17.8, is that the final answer? 17.8? Impossible. Why? Impossible because it doesn't have to do with pH. It has to do with something else. The whole thing about recognizing. You see, the thing is, it's impossible. Why is 17.8 impossible? In fact, even 14.6 is impossible because I'm sorry? Oh yeah. It's impossible because if you double this, what does Le Chatelier's principle say? If you double the hydronium concentration, the equilibrium shifts to the left. And so these values, are they going to be valid anymore? No. So if we double the hydronium, we need to shift this. So should we go back and shift it using Le Chatelier's type calculation? No, because endless loop, right? We're going to be in an endless loop. And so that is called full credit for simultaneous. If you can recognize that this is this has to be solved simultaneously, then that's important. You know, you cannot use stepwise.
So the low concentration of the weak acid would give you a hint.
Yes, right. Low concentration of strong acid. If you want to go for patterns, low concentration of weak acid, okay. What about low concentration of strong acid? Did you memorize that?
Yeah, you have to consider the
Can you do it stepwise?
Yeah, you can.
Okay.
But you have to, water is going to contribute a lot of hydronium.
Good. So if you recognize those patterns, you're good.
For the test, if you give us the test simultaneous, did you just want us to recognize it and like write it down, or did you want us to actually try and solve it with like the watch instead?
I want you to try and solve it, but trying to solve it is advanced level. Not everybody is advanced level, so it's okay. That's why there's some problems I expect, advanced level problems I expect everybody to do, but simultaneous is one of those. Maybe, maybe not. You know, maybe not, because, you know, simultaneous, you just have computers do the simultaneous calculations. You know. You use software packages to do simultaneous. But it's good just to do a very, very simple simultaneous. A very, very simple simultaneous would be like this. You know, the equilibria that actually happen in natural waters is much, much more complicated, you know, because you got so many equilibria that interact with each other that all have to be solved simultaneous. So just having two equations and two unknowns is manageable, but when you have many equations, then and so you should be able to do the basics simultaneous, but I decided it's going to be a bonus because that takes too much time, and I don't want to wait around for everybody to finish it or try to finish it, which could take potentially hours, you know, after, because the algebra is not so easy. So I tell people just to go ahead and do this. Yeah.
I just had a question about the problem you just said. We're doing KW, right? But we're solving for KA. Because I get how you got x squared plus 7.8 times 10 to the negative 8. But I wouldn't know to put that 1.0 times 10 to the minus 14, which is the KW, right?
Yeah, you have to memorize it.
I know, I memorized it, but how would I know to input it there? Because when I look, you know, you guys see.
Oh, because I didn't write it over here, right?
Oh, okay.
And so I just, you know, multiplied x throughout here and then subtracted this to set it equal to 0. And so I just rearranged it. It was there all the time. I just didn't write it down. Uh-huh.
The only K values you have to know would be water, right?
Yeah.
The other ones would be given.
Right. All the other K's are given.
Like golf system.
Except for water and strong. Not just strong acids. Strong acids, strong bases, and soluble salts. Those all have very large K's.
So we don't have those.
You have to have those memorized.
Well, we have to know.
Yeah, memorize is very large. I know, it's not so funny because oftentimes I'll give something like HCl and I don't give the K value. And during the test, 3 or 4 people will come up to me and say, there's no K value given. How can we solve this problem? We can't solve it. And then I tell them there's enough information there to solve it. If they have it memorized. If they don't have it memorized, then let's see, they set up the ICE table and just leave the X unsolved. That happens all the time. I see it every semester. All right, so, recognizing it and then setting it up simultaneous. So that was the question. How do you set this up simultaneous? You set it up just like we did the last one. So you use the ammonia one as a template and then just do this one. So we're doing this one, so just set it up just like we did the ammonia. Just look at your notes and tell me what to write here. Or better yet, don't look at your notes. Hopefully you've reviewed your notes more than once, or at least once, and then you can just, because the more times you see it, the more you'll be able to recall it. And so do you know what I'm going to write here? What should I write for HCN?
The concentration given.
Yeah, 1.0 times 10 minus 5.
Nothing.
Water is nothing.
Hydronium X.
Hydronium X? I differ from the book, The book uses, because I want the first one, X to represent the change here. So the book will use X here. I use Y because it matches more. What about cyanide? 0. Okay, then the change, this is why I use Y here, because I want the change to be in the first one, minus X, plus X, plus X molar. And so at equilibrium, I have 1.0 times 10 to the minus 5 minus X molar, Y plus X molar, and X molar. Now, if you're getting stuck here, you want to ask yourself, what's making you stuck here? Maybe it's not being familiar with it enough. Maybe it's not seeing it enough times, But like I said, I'm only going to hit you with the easiest or the simplest simultaneous. And the simplest simultaneous is going to have the exact same setup. Right? And so ask yourself why you would be getting stuck here. Well, it could be, what do I use here? Y or X. It actually doesn't matter, as you can see from the book. Now here, what do I do here? Hydronium is going to be X. Hydroxide, 0. And then you change, plus Y. Okay. Now we have it, right? The basic setup. And so this is already partial credit here, right? You're already getting some partial credit. Bonus credit, I mean. Partial bonus credit. Not full bonus credit. But you could do more. Is this, this is not too bad, right? Once you've seen it, let's say you've seen it like a dozen times. If you've seen it a dozen times, imagine how easy it is, right? but the problem is most people have only seen it once in lecture and never seen it again, you know? And so it makes it a lot easier. So Ka is equal to
6.2.
yeah, 6.2, but we'll do y plus x times x divided by 1.0 times 10 to the minus 5 minus x, correct? Kw is equal to x plus y times y. Okay, now this is why I made this a bonus. How do you solve for x? Or how do you solve for y? We got two equations and two unknowns, so it seems like it should be easy, right? 1.0 times 10 to the minus 14, and you know, so what is this? 6.2 times 10 to the minus 10. It seems like it should be easy. But it's not. So how do you solve this?
If you just name the H3O plus concentration different letter like Z, and then say Z is equal to X plus Y.
You could do that. Oh, that's how you did it?
Yeah, it makes it a lot easier. So.
Okay, that sounds good. And so you did Z is equal to X plus Y?
Yeah.
Okay.
And that way it's out where you're getting K equation draw.
Oh, I see. And so this would simplify into Zx over 1.0 times 10 to the minus 5 minus x.
Yeah.
And over here you get Zy equals 1.0 times 10 to the minus 14. That's good. Okay, then what did you do next?
Solve for y and x, and then plug that into Z is equal to X plus 5.
Okay, so like here you would solve for y. Y is equal to 1.0 times 10 to the minus 14 over z. That's not allowed?
You can plug that in for y. Z is equal to
Okay, and then plug this in for y over where?
into Z is equal to X plus Y equation.
Oh, into the z is equal to x plus y equation. Here, so you would get x plus 1.0 times 10 to the minus 14 over z,
Yep. And we do the same thing for X.
and then the same thing for x.
Only you can use, I think you can use the simplifying assumption on the equation of 10 to the minus 5 minus X. Or, yeah, well,
Here to get rid of the x there.
Then how's the C value for that? With Z as an X, you're already assuming that X doesn't exist.
So you did the simplifying assumption.
yeah.
Okay. Hmm?
You can't use the simplifying assumption.
No, I didn't say you can't do the simplifying assumption. Actually, we saw the simplifying assumption. It actually worked in this case, you know, when we did step 1. That's because the hydronium, sometimes you can't do the simplifying assumption because it will not work. Either the concentration is too low to begin with. If you don't use the simplifying assumption, could you still solve it?
It would be a lot more difficult.
Yes, it's a lot more difficult. And so you're right, you would have used the simplifying assumption, and the book does use it in their example. And so here, we just say etc. Go ahead and go through it if you'd like. Did anybody else solve it? Hmm? I'll tell you, without the simplifying assumption, it's a bear to solve. Okay. But do you want to spend hours doing this? You know, it's only if you have the luxury of time. And so that's why it's a bonus. Okay. But setting it up is good. You know, set it up and get it as far as you can. If you have time, go ahead and do that. Although tomorrow do I have to leave early? No. Is that okay? That's enough. I mean, the rest is algebra, right? Difficult algebra, but it's algebra. See, you know, for you algebra pros, see if you can do it. All right, other questions? On this? So the setup is the same. Rather, this is a acid instead of a base, so we're doing it based on hydronium. For bases, we do it on hydroxide instead of hydronium.
What if you had a polyprotic acid?
What if you had a very dilute polyprotic acid? Yeah, if you had a very dilute weak polyprotic acid, you're going to have a lot more work. All right. Any questions? Any other questions from chapter 16? I was going to try to hand back your chapter 15 test today, but it looks like I'm going to get it back to you tomorrow. I posted the key to the chapter 15 test, so you can see at least the key. It's on Piazza. For the chapter 16, that practice test, usually I don't like to post the key because, people get in the habit, and me too, they get in the habit of always being able to look up the answer in the solutions guide, or always being able to ask somebody, is this answer the right answer? The teacher or whoever else. But pretty soon in science, you get to the point where, the answer book isn't there, or, there's nobody to ask if this is the right answer. And so you have to start thinking about, how do you have confidence that your answer is correct? And so how you have confidence that your answer is correct is you would, double check it, redo it, that kind of thing. You want to get that kind of confidence because, that to generate that kind of confidence, then you can go into the solutions guide and say, oh, wait, it's wrong. The solutions guide's wrong, or the book is wrong, I did it correctly. Or the exam, the exam is wrong. There's a problem with the exam. You can come up and tell me. Because, everybody has the potential to make mistakes. All right, let's take a look at some chapter 17 problems. And we're just looking at different mixtures. And so I looked at some acid-base mixtures. The acid-base mixtures are called titrations. The titrations. And these titrations can lead to other mixtures. Other types of mixtures. So we have acid-base mixtures, and then what we're going to have is acid and salt mixtures. Like an acid and salt mixture or base and salt mixture. Acid and salt mixtures, these are common ion. In common ion, you know, we have different types of common ion mixtures. You know, one is just a simple mix, but another type is a buffer mix. The simple mix is just, what I mean by that is it's not a buffer. We have salt and salt mixtures. You guys know what a salt is, just an ionic compound. Okay. Salt. So let's take a look at some common ion problems first, and then buffers, and then titration. A common ion problem would be like this, a mixture of HCl and sodium chloride. Common ion here would just be chloride. Or, you know, we could have HCl and acetic acid. HCl and acetic acid, the common ion would just be the hydronium. And we'll see what we do in situations like this. And so in simple ones, you know, simple common ion, we just add up the common ion. Let's say we have a mole here and a mole here. We're going to end up with 2 moles. In more complex common ion problems, then if we have a mole of HCl and a mole of acetic acid, are we going to get 2 moles of hydronium, 2 moles of H+? No, because yeah, this is a weak acid, right? And so we have different types of mixtures depending on what we do. So let's say I have a solution that is 0.100 molar HCl, and at the same time it's 0.100 molar sodium chloride. Okay, this is what I call a simple one because it's just additive. You know, if we have, which one has a bigger K, sodium chloride or HCl? Well, they're both very big, right? Very big K. So it doesn't matter. Which one do you want to start with, the sodium chloride or the HCl? The HCl. All right. If we do the HCl, we got HCl plus water gives us hydronium and chloride. And so we know that K, actually you should have K for this memorized, very big. So we end up with 0 molar water, we don't do anything. 0.100 molar hydronium and 0.100 molar chloride. Now if I want the solution inventory for this, then should I do step 2? Yeah, I guess I should do step 2 to figure out how much additional hydroxide I have. But I probably should do sodium chloride. All right, let's do sodium chloride. So if I have sodium chloride is a strong electrolyte that's going to produce sodium ions and chloride ions. K for this is going to be very big, so I'm going to have complete conversion into the ions. Except now, this is going to be 0.100, right? This is 0. 0.100 is going to be 0.200 molar at the end. Okay, does this perturb the previous step here? Why not? I just doubled the chloride. Why doesn't it perturb it? It has a large K value, meaning it can't be perturbed. It's going to be a one-way reaction. And so even though I doubled this, it's not going to impact this previous step here. Okay, there's one more equilibrium that's happening in here, and that's
Water.
Kw, water. So if I do H2O liquid, plus H2O liquid, your book does this more quickly because water is just going to tell us how much hydroxide is generated. And so what your book does is they assume that the amount of additional hydronium is negligible and use the simplifying assumption automatically to calculate the hydroxide. What we'll do is we'll set it up. And so this is going to be 0.100 molar, 0 molar, initial change, equilibrium. So at equilibrium, we're going to have 0.100 minus X molar and X molar. Is it okay if I skip that? Plus X, yeah. And then, you know, if we look at KW, KW is going to be 0.100 plus X times X. Your book does the simplifying assumption automatically and just plugs in 0.100 here times X, right? And so if you look at the solutions guide, it always goes straight to this, which should be totally valid in this case. So X is 10 to the minus 13. Right? So the X is 1.0 times 10 to the minus 13 molar. And that means 0.100 plus X is going to be about 0.100 molar, just slightly above it. Right? All right, so when we're doing solution inventory, this is simple because everything just adds up. You know, the total hydronium is going to be a little bit above 0.100. The total chloride is 0.200, and the total hydroxide is 1.0 times 10 to the minus 13. And the sodium, sodium is 0.100. And so when we do the solution inventory for this mixture, these are the species we're going to find in solution. Sodium ions, 0.100 molar. Chloride ions at 0.200 molar. Hydronium at about 0.100 molar. And hydroxide, 1.0 times 10 to the negative 13. So we got the inventory for that mixture. All right, now if we do this second mixture, this is a more complicated mixture. It's not just simply adding each step, like put, you know, step 1 plus step 2. But it's not anything more complicated, you know, because if I have an HCl acetic acid mixture, you know, where should I start? Because there are 3 equilibria. I have Ka for HCl, I have Ka for acetic acid, and I have Kw. So we want to do these always in a stepwise fashion, right? And so we do HCl first. And so if we do HCl, let's make this 0.100 molar in HCl and 0.100 molar in acetic acid. So here, am I going to get 0.200 molar H plus? Yeah, there's no way because acetic acid is a weak acid. Not only that, but it's going to be inhibited by Le Chatelier's principle. In fact, how much additional hydronium do we expect from acetic acid?
Not much.
Not much. And so let's take a look. So HCl here, HCl plus H2O liquid, this is going to give us hydronium plus chloride. And so initial, this is standard, 100 molar, 0 molar, 0 molar. Change is going to be complete, so we end up with 0 molar, 0.100 molar, 0.100 molar. And so from step 1, this is what we get. Now we go to step 2. Step 2 is going to be, well, acetic acid. How much additional hydronium are we going to get? And so in this case, it's similar to a diprotic acid, right? Like if you have a diprotic acid, step 1 is, you know, the Ka1. Step 2 is Ka2 for the diprotic acid. Except this is different because now we have 2 monoprotic acids, but it essentially is the same setup, same kind of calculation. we're saying, you know, for this weaker acid here, how much additional hydronium are we going to get? And so we got H2O liquid. This is going to go to hydronium plus acetate. And so initial acetic acid is going to be 0.100 molar. Initial hydronium will be 0.100 molar. And acetate, 0 molar. Now how much hydronium do we expect? Yeah, minimal hydronium. Why? Why do I expect so little hydronium? Not because it's a weak acid. Because there's already 0.100 molar hydronium here to begin with. If this were 0 and 0, I'd expect a lot more hydronium. You know, acetic acid, 0.100 will bring the pH down to 4, 3. I forgot. Exactly. But we can figure it out. Here, and so the change, this is going to be minus X molar, plus X molar, plus X molar. And so equilibrium, we're going to get 0.100 minus X, 0.100 plus X, and X molar. So Ka for acetic acid is 1.8 times 10 to the minus 5. Acetic acid is a common acid, so this is why it's easy to remember. Hydronium times acetate divided by acetic acid concentration gives me 0.100 plus X times X over 0.100 minus X. I would expect the simplifying assumption to work quite well here because of the huge initial concentration of hydronium. And in fact, this is going to equal X. And so that means that the percent change is going to equal 1.8 times 10 to the minus 5 over 0.100. It's 10 to the minus 1, 10 to the positive 1, 10 to the minus 4, 10 to the minus 2. And so this is going to be a 0.018% change. And so that's fine. There's no problem with that. And so here, you know, if I was interested in the pH of the solution, only the pH, if I was interested in the pH of an HCl and acetic acid mixture, would you do 3 steps?
No.
Would you do 2 steps? No. Yeah, you know, when you have a strong acid and a weak acid, the strong acid is pretty much it. You could just do step 1, right? You get the exact same pH as you would if you incorporated, or you know, almost the exact same pH. You know, when you round it, it would be the same.
Wouldn't water contribute a lot of hydronium in this case?
Would water contribute much hydronium? No, for the exact same reason. The reason, okay, let's go ahead and calculate the hydronium here. So it's going to be 0.100 plus 1.8 times 10 to the minus 5. So it's 1, 2, 3, 4 zeros and a 1/8. So we got 0.100 sub 0.18. Yes, it did contribute a little bit, but do this. Calculate the pH here. pH is going to be 1.000. Calculate the pH here. Did it change the pH significantly? What's the pH that you calculated here? 0.999 how many nines? 4. Now we're only allowed 3 sig figs, so you gotta round it to 1.000. And so do you see we're gonna get the same pH that we would have gotten? A little bit different because we do get a little bit of hydronium. Now will KW add significantly to that? And I would say definitely not, because why? It's not necessarily, KW is small for one thing, right? But your initial, look at the initial. It's so big. You know, how much more hydronium are you going to expect? Not much. And so, if you're interested in the pH, then we do just the first step. That is assuming that, you know, it's concentrated. You know, if this were like this, if I made the HCl 1.0 times 10 to the minus 9 molar, then that changes the whole dynamic of the problem, right? Because this is almost like pure water. And so really, you would treat this only as a acetic acid solution. I mean, you would add to this, but you'd say probably, you know, water is going to contribute a comparable amount of hydronium as HCl. You know, and so this is more of an acetic acid. But as long as the concentrations of the two are roughly, you know, comparable, then you know, the strong acid dominates.
In that case, would you still do HCl first? Yeah,
I'd still do HCl first. In this case, I definitely would do HCl first. HCl has the biggest K. And then acetic acid is going to generate a whole lot more hydronium. A whole lot more, but it will not perturb HCl because K is very big. And so do you see, this is just kind of like similar to what we've been doing in chapter 16, you know, the polyprotic, right? In that sense. Now, it depends on how big. A weak acid might contribute here if it's fairly strong. So if I had HCl and phosphoric acid, then I might start to worry, because phosphoric acid is quite a bit stronger acid than acetic acid and might actually contribute something significant. Does that make sense? Or some other fairly moderate strength acid. You know? And so this is all, but we can do the calculation just to be sure. If you're ever uncertain, it's kind of gray area, then do the calculation. But after you've done a bunch of these, then you see, oh, I can ignore this. Just look at this for the pH. Just comment on it. Okay, I'm going to do another common ion for you. You know, it's basically the same kind of techniques. In this next example of a common ion, we're going to look at 0.100 molar acetic acid, and the solution is also 0.100 molar. Let's pick another acid. Benzoic acid. Benzoic acid has a benzene ring stuck to the carboxylic acid group. It's called benzoic acid. All right, so acetic acid has a Ka equal to 1.8 times 10 to the minus 5. Benzoic acid has a Ka equal to, I'm going to just use the books, 6.5 times 10 to the minus 5. Is that it, Arthur? Can you, bottom left? Okay, now I start with the biggest K value, right? What is the biggest K value? Benzoic acid, right? Benzoic acid is a stronger acid, so let's go ahead and do that. C6H5COOH. Is this problem worrisome at all? Does something bother you about this problem? Potentially? Yeah, you know, it looks like the two Ks are roughly the same, which means what? They're going to both contribute hydronium, and they're both going to perturb each other, which means simultaneous, right? But if you're uncertain about simultaneous, what you do, you try to do it stepwise and see if simultaneous is required. So let's go ahead and do stepwise here first. We got hydronium, that's C6H5COO minus. So initial is 0.100 molar, 0 molar, 0 molar water. All right, what do you think? Should the simplifying assumption work? Yeah, probably work. I mean, we have pretty big concentration here on 100, so you might as well try it. And that gives us an X value of 0.0025154. And actually the numbers are simple, so this is a 0.254% change. So it's okay.
It's 2.5.
Oh, sorry, 2.5. Not so simple. 2.54%, which means borderline. I mean, our cutoff is 5%, or was it 5% or 6%? 5%, so that's halfway to our cutoff. But we'll go ahead and use it, because we just know it's going to be a little greater error. If we had the luxury of time, we could do the quadratic to get a little better answer. But if we don't have the luxury of time, this is perfect't adequate. And so I get 0.09746. Only 2.5% hydrolysis. It's a pretty weak acid. We should do what? Just double check it just to make sure it checks out. Is it okay?
6.6.
6.6. I expected it to be off anyway, but 6.6 seems okay. 6.6 what? I mean 6.6 in 1? Okay. And so that's okay, considering, you know. I'm sure if I did the quadratic, I'd get better K value. Yeah. All right, now what do we do? We go to step 2, which would be the next biggest K. So the next biggest K is going to be acetic acid. Let's go ahead and do that. Acetic acid, used to a liquid, it's hydronium plus acetate. Initial acetic acid, initial hydronium, and initial acetate, change. Solid K is 1.8 times 10 to the minus 5, which is going to equal, you know, the hydronium, the acetate, set it up, whatever is the acid at equilibrium. So 0.00254 plus X times x over 0.100 minus x. All right, just try the simplifying assumption. If you do the simplifying assumption, the math gets a lot easier. So it goes 0.00254 times x over 0.100, which means x is equal to what? 1.8 times 10 to the minus 5. 7.2 times 10 to the minus 4. Now we calculate the percent change. So what is the percent change? Is it going to be x over 0.100 or x over 0.00254? 0.00254. We want the bigger percent change. So this is going to be 7.2 times 10 to the minus 4 divided by 0.00254 times 100%, which gives us, what is it? 28%. So it fails. So we're going to have to do the quadratic for this. Let's go ahead and do the quadratic. So getting this, so it's going to be x squared plus 0.00254x is equal to 1.8 times 10 to the minus 10 minus 1, 10 to the minus 6, okay, minus 1.8 times 10 to the minus 5x. So we got to add 1.8 times 10 to the minus 5 both sides. So this is going to be x squared, x plus 10 to the minus 8 would be 4 zeros and 1 8. This is going to be 0.00255 x minus 1.8 times 10 to the minus 6 is equal to 0. You have a quadratic solver.
5.74 times 10 to the negative 4.
X equals 5.74 times 10 to the negative 4. Okay. And so this is going to be 0.100 minus, we need 3 zeros, 5, 7, so 4. So we got 3 more zeros there. 10, 6, 9, 8, 4, 9, 9, 0. 0.099426 more. 0.00254 plus 3 zeros, 1, 2, 3, and then 574, 574. Another 0 there, 2, 4, 11, 3. And this would be 5.74 plus 2. So what should we do next? We should double check. Yeah, let's double check K. See what we get. It works? All right, so we're good. What is the total hydronium concentration? Do I add the hydronium I got from step 1 plus the hydronium I ended up getting in step 2? Do I add those two together?
Yeah.
No, because I already did. I mean, here's the hydronium from step 1 being added to the hydronium in step 2. And so this value is no longer valid, right? what is the current hydronium in the solution? It's this. Now, do you see the problem? What's the problem? This means the hydronium increased here, which shifts left, which means endless loop, which means simultaneous. However, this simultaneous is more difficult because this is 3 equations. What's the third equation? Water. I mean, we might say we could ignore water, which is probably pretty good, you know. But technically, we should include it. So, so you recognize that, right? Does everybody recognize that? And so, do you see we're just repeating the same calculations over and over again with different systems, you know, different mixtures. Some of the calculations can be greatly simplified. You know, well, actually, let's do another one. Let's do another one like this. The next example is I'm going to take, let's take HCN. Hydrocyanic acid you want to avoid never making this stuff because it's very toxic. You know. Cyanide. What makes hydrogen cyanide so toxic? Is it because it's a powerful acid? Well, redox is a pretty good reducing agent, cyanide. But it's not because of its redox, it's because of its metathesis properties. No, you know what makes it's because of its Lewis. Hydrogen cyanide is considered a very good Lewis base, not an acid, and it's the cyanide, you know, that does it. Cyanide attacks, you know, iron 2 in your hemoglobin and binds very tightly, forms a very strong coordinate covalent bond and doesn't let go. Once it binds there, then O2 can't bind. And so it's extremely toxic. But it's a weak acid. And let's try to neutralize this. We're going to try to neutralize this with ammonia. Ammonia. And so what forms here? Yeah, cyanide and ammonium. What is K for this? Would you say K is very large? It's an acid-base neutralization? No, you'd expect it to be small because you wouldn't expect it to completely neutralize each other out. Weak acid, weak base combination. And so how could you solve this particular problem? I want to know what the pH of this is going to be at the end. It turns out that K is small, which means that if K is small, that means that what? Yeah, it means that both of these coexist to some extent. Yeah, actually with these as well. These species coexist, you know, at some equilibrium. And so for problems like this, unfortunately, because you got to do, if you want to figure out the pH, what do? You look for the hydronium ion generators, HCN and ammonium, and you look for the hydroxide ion generators, which would be ammonia and cyanide. So what should we do? If we have some kind of coexistence with this, we got to figure out the equilibrium values, and then we got to figure out the, how much hydrolysis do we have to generate the hydronium and the hydroxide to dictate what pH is, right? And so the problem like this is, even though this seems so simple, it is not simple. This is pretty much, it doesn't look simultaneous in a way here, right? But this is simultaneous. Simultaneous. This is called a buffer solution here. Why is it called a buffer? It's called a buffer solution because it contains acid and base in the same solution, not in the same proportion. They don't have to be in the same proportion. It just has to contain acid and base in significant quantities in the same. So if I made this 0.100 molar, 0.100 molar, I'm still going to get about 0.100 and 0.100, right? And so what that means is, if I add strong acid to this, you know what's going to happen? The ammonia will attack the strong acid. If I add strong base to this, the HCN attacks that. And so we have this coexistence of a weak acid and a weak base, in which you can add strong acids and strong bases and have their effect neutralized. That is, it'll neutralize the strong acid, neutralize the strong bases, and maintain a fairly stable pH. That's what a buffer is. It buffers the pH changes. But this is a difficult buffer, because this buffer consists of two different acids and bases. And so this is a buffer, we call it buffer 1. Simultaneous. This is another kind of buffer solution here, called buffer 2. Buffer 2 would be something like this: sodium, hydrogen, carbonate. Sodium hydrogen carbonate. What is the pH? For example, why do I call this a buffer? What is the pH of this? Why do I call it a buffer? Because bicarbonate is amphoteric. And so bicarbonate can act as an acid, and it can act as a base. Bicarbonate acts as both an acid and a base. So how do I calculate the pH of this solution? Well, it's easy. To calculate the pH, acid hydrolysis forms hydronium and carbonate. So I'll just go ahead and calculate how much hydronium is generated and then determine the pH from that, right? But there's a problem. What's the problem? It can also collide with water to form carbonic acid and hydroxide. So what happens here? Does the hydronium generated here in this collision cancel out the hydroxide generated in this collision? No. The only time they cancel each other out is when the K values are equal, and that only happens for, it happens for one species. Tell me what one species the Ka and the Kb are equal. Water. And so water is pH neutral, but in this case we got to look at the Ka. And so we look at the Ka for bicarbonate. What is the Ka for bicarbonate? 5.6 times 10 minus 11? And what is the Kb for bicarbonate? Kb for bicarbonate is equal to Kw over the Ka for what acid?
Conjugate.
Yeah, what is the conjugate acid of bicarbonate? Carbonic acid. So this is 1.0 times 10 to the minus 14 divided by the Ka for carbonic acid, 4.3 times 10 to the minus 7. Which equals
2.3 times
6. So what do we generate more of? Hydroxide or hydronium? We generate more hydroxide. So bicarbonate should have a pH that is greater than 7. So what is the pH? Now the thing is, let me ask you how we can solve for the pH for this. Because we generate more hydroxide here, but what about this hydronium? Will the hydronium neutralize out the hydroxide we just generated? Or how's it tied together? What is the best way to solve for the pH of this mixture?
Find the pOH and subtract 14.
Okay, we find the pOH, and so we only do Kb and we ignore Ka. That's one option. We could say that Ka is so small, we'll just ignore it. But no, that's not the way we're going to do it. We have to worry about Ka, because Ka is going to generate hydronium, which is going to alter the pH. And so what's the way to solve this? The only way to solve this is... Sorry, I forgot to turn off the volume. Nice little run there, but again, right at opening price and lower. All right. Do you see the problem here? If you solve this one, then we have to worry about this one. But in order to worry about this one, how is hydroxide and hydronium tied together? Hydroxide and hydronium are tied together by Kw. And so what happens here is this. We have to do simultaneous. With the Ka for bicarbonate, the Kb for bicarbonate, and Kw. Are we going to do that in this class? Huh? No, we aren't going to do that in class, but somebody did that for these. For this system, it simplifies. If you do the simultaneous for this type of system, then, and we make the simplifying assumption. We make some assumptions. We can generate this simple equation. The pH for an amphoteric is equal to the pKa for the amphoteric plus the pKa for the conjugate acid of the amphoteric divided by 2. And so some of the assumptions that we make is, 1, we have fairly high concentrations of the amphoteric. 2, the simplifying assumption holds. And then what we can do is we can take the simultaneous and simplify it into a very simple algebraic expression like this. And so this is these are some complicated mixtures here because we have to do these simultaneously, right? We'll look at another buffer, buffer 3, in which we don't have to do it simultaneously. And in fact, stepwise works fine for it. And we'll look at that next. It's called the common ion buffer. I'll stop here.